I would like to introduce Jeffrey Zhang, who will be presenting Multipath Traffic Engineering on behalf of Caridi Campella. Jeffrey is a senior distinguished technologist in HPE's routing protocols team, and he's also been a really valuable member of the program committee for the last 2 years. He has traveled from Boston, Massachusetts to join us today for his third presentation at NANOG. His previous presentations were at NANOG 81 and 90, both on multicast. Welcome back, Jeffrey.
Thank you, Adair. Good morning. It's my honor to be back here on the NANOG stage, this time presenting Multipath Traffic Engineering for WAN and AIDC on behalf of Caridi Campella. NANOG has been long time focused on network infrastructure for a long time, and this NANOG 96 has a spotlight on AI. So there's no better venue to present this multipath traffic engineering. And that's why when Caridi got pulled away for another engagement, we decided to continue this presentation, and I got to do this job. Hopefully, I can do a decent job, don't let too many people down. So I will talk about history of traffic engineering briefly, its toolkits, enhancements, and the recent multipath innovation, and the applicability of MPTE to the AIDC. I will then talk about the concept of the MPTE, how it works, and the signaling options, including both BGP signaling and RSVP signaling. I will then end with the takeaways and a brief update on the current status of this innovation. I want to first start with the goals and tools of network optimization. Generally speaking, whether you're a WAN or DC operator, you want your network to have high utilization, nearly congestion-free, so that you can provide low latency, low loss traffic delivery, and you want your network to be resilient. It's similar goals for both. Of course, with AIDC, it's even more critical to achieve that, because AI workloads are sensitive to congestion and latency. The GPU pipelines stall when even a single packet gets delayed or dropped. To achieve those goals, you can use non-shortest paths when necessary. And you want to use bandwidth reservation to guarantee that your path will not get congested. And you want to use the alternative paths, backup paths, for the resiliency. And traditionally, traffic engineering with bandwidth reservation is a de facto tool to achieve those goals in the WAN. But it does not support multipaths, and it has not been adopted in the data centers for good reasons. And traditionally, traffic engineering are very much associated with MPLS. Back in 1998, when MPLS was introduced in IETF, it was with the goal of providing traffic engineering. RFC 2702, Traffic Engineering Requirements, was published in 1999, I believe, and productizing MPLS was Cariti's first task in the routing protocols when he was in Juniper. A few things have changed over the course of 27 years. The fundamentals remain the same. We have the auto bandwidth, a big step forward, making it easier to spec bandwidth and more useful. And forwarding adjacencies allow us to build hierarchical TE more easily. Today's network now offers fresh perspectives on the need for load balancing and traffic engineering. And still, the MPLS could bring something novel to the table and change the way how we engineer networks for AI workloads. Generally speaking, there are two camps of operators: those who like, need, and deploy traffic engineering, and those who don't. So why do traffic engineering? For people in the traffic engineering camp, they want to better utilize their network capacity. They want to handle the faults and network outages to get more insights into the traffic patterns, and with the end goal to improve end customer experiences. For the other camp, they can just throw bandwidth at the problem and use ECMP to provide the resiliency. They don't need to care about traffic patterns. Things will just work out well. It's understandable that many people have concerns with scaling and OpEx overhead of managing so many traffic engineering tunnels, paths, and policies. But I do want to point out that with modern control plane and data plane, we can handle the scale and churn much better. Today's telemetry analysis insights are huge and necessary for AI ops, and we have much better management and automation tools. From many presentations we have seen, even in this analog, AI workloads also benefits from traffic engineering, and sometimes they need traffic engineering to help. And so to do traffic engineering or not is no longer a question. So now it's a brief review of the toolkits that we have been using for traffic engineering in the WAN. Auto bandwidth enabled LSPs. So basically, when you deploy traffic engineering, you can monitor the actual traffic on the LSPs. You collect the statistics, you estimate the bandwidth you need for your LSPs, and make optimizations to accommodate that. That works very well in practice, but there is still one difficulty to place fat LSPs in the network, what we call the bin packing problem. You need either manually provision of additional LSPs between the same pair of ingress and egress nodes, and you do the load balancing at the ingress. Now, if we look at this picture here, between the router 1 on the left and the router 14 on the right, let's just say that any of those paths can only give you 10 gig bandwidth, but your aggregated bandwidth requirement is 50. What do? Manually configure those additional LSPs will help, but the container LSPs, or TE++, as we call it, allow you to manage those member LSPs that give you the more aggregate bandwidth automatically. That improves the bin packing without need for additional provisioning efforts. So basically, you will create dynamically multiple LSPs as you need, and you can tear it down as if you don't need it anymore. It allows the elastic sizing of the member LSPs and creation and removal of those member LSPs. Still, today, the load balancing only happens on the ingress, and typically it's equal or weighted load balancing on the ingress. There is no intent to maximize the multipath, and more importantly, those individual member LSPs causes a lot of signaling, because each member LSP will have its own signaling states. In this example, to cover all those possible paths between router 1 and router 14, you would require 30 member LSPs. And that involves 360 messages on the wire. And on the router R4 and R8, they each maintain 30 path state blocks and 30 reservation state blocks. There are some other notable traffic engineering tools. I will not get into the details of that, because unless you are an operator that actually deployed the RSVP traffic engineering, those are probably the details you don't care. Now, finally, let's get into the MPTE, multipath traffic engineering. The first thing is that adding the multipath to traffic engineering, as we that is more in the WAN side. If we look at this picture, we have a network and with routers, and there I have 4 fat pipes between R1, R2, R3, and R4. And then we have other thinner links for the rest of the network. Assuming that all the link metrics are the same, then when you use the shortest path routing, you can only get 400 gig from R1 to R12, going through that shortest path in the middle. Now, if you use conventional TE, you can achieve 1600 gig through between R1 and R12. You do that by creating 4 LSPs, either by manual provisioning or use the TE++, the container LSPs. Top one, 400 gig, middle one, bottom one, another bottom one. As we mentioned earlier, this incur a lot of signaling in the network. Now, if you use multipath TE, you only need one MPTE DAG construct to achieve this. DAG stands for Directed Acyclic Graph. It's basically sort of like a tree starting at the ingress and then eventually converging back into the egress. The DAG can branch and recombine as needed. In this picture, R1 can split the traffic 2 ways to R2, and R2 can split the traffic 3 ways, with 50% of the loads going to R3 because it has a fat pipe there, and then 25% to R7 and R9 each. Automatic adjustment of the DAG and its branching ratios can happen when link on the DAG goes down temporarily. But the shape of the DAG remains unchanged unless there is a permanent change to the topology. In this example, when R4, R6 link goes down, the traffic is switched from R4 to R5 100%. But this is just a local change. The rest of the network is not disturbed. The routes on the ingress that sits on top of that tunnel does not have to change. Now, like conventional traffic engineering, you can still use constraints. For example, those top paths in the purple color, I don't know if you can see clearly, can be excluded in your in the calculation for that DAG. You can even have multiple egresses. Right now, we have a DAG from R1 to R12 only. Suppose you have R15 there, just as good as R12 as an egress. For example, you have VPN multi-homing, or you have IBGP multipath. You can add that R15 to the DAG as another egress. And you only need to touch the routers upstream of R15, in this case, R11, R8, R5, and R6. You can update the state on those routers so that they can split the traffic to R12 and R15. Now, this is a summary of the key differences, differentiators, or attributes for MPTE, Multipath Traffic Engineering. It enables equal cost load balancing at every junction on the DAG. It supports multiple ingresses and multiple egresses. We gave an example of the multiple egress. Multiple ingress could also work, but the multiple egress is generally more practical. The multipath spread is maximized in the provisioned DAG within practical constraints. Amount of state that is needed to set up the DAG is significantly less compared to using the member LSPs of container LSP. If you have a resource failure, degradation, or traffic demand change, the amount of churn that is involved is significantly less, and the shape of the DAG is largely static post-setup. We don't do unnecessary addition, deletion of the branches in the DAG, and we do not need to touch the routes or next hops at the ingress that use this DAG. We can automatically adjust the junction bandwidth and the next hop's load share. Now, for the second part of MPTE, adding traffic engineering to multipath. If you look at this cloud network, a part of an AI/ML cluster, in fact, this is just a partial cloud network. It's canonical multipath network, very structured, as symmetric as possible, with the lots of multipaths. All the links and nodes, they have the same cost, capacity. You do equally weighted multipaths on each node. Now, can this network, which is purpose-built for ECMP, can the TE help here? Well, if your entire cluster is working on a single training task, you probably don't need the traffic engineering here. But if your cluster is split among multiple ML training or inference tasks, then traffic engineering will help. For example, you have the blue jobs and you have red jobs. The bandwidth and weights for load balancing for the blue or for red jobs will depend on the blue workload or red workload. You basically color your network and your CPU, GPUs, and reserve resources by task. Oh, by the way, I started with the AIDC, and now we're talking about AI/ML cluster. I just use it interchangeably. So in this case, if you do traffic engineering without multipath, it's a total non-starter. From many presentations, we have seen that the spend on the compute resources dwarfs that of network. But still, the network appears to be an outside source of problems, of GPU stalls, job delays, or even aborts. That requires us to take a new approach here. And notice that AI ML workloads are scheduled. How many CPUs, how many GPUs, how much memory does a job need? Where do you place them? Those are handled by the job scheduler. We can add traffic engineering to enable network scheduling that goes along with the job scheduling. You probably noticed that the vendors and operators have spent a lot of effort addressing the congestion problem in the AI/ML cluster. Typically, a reactive approach is taken. We detect, signal, and react to congestions. Here, we're trying to take a proactive approach. We get a holistic view of the network utilization to make resource reservations to avoid congestion ahead of time as much as possible. In addition, we add mechanisms to detect and react to the congestion that may happen. Also, reinteract to the failures. And so this proactive approach is a new conversation starting in the IETF routing area working group. We have proposed to use the MPTE for resource reservation, protection, and traffic isolation. So finally, let's talk about some key concepts of MPTE. We already talked about DAG, Directed Acyclic Graph. Here we just call it MPTED, basically MPTE DAG. So there's also a concept of the tunnel. MPTED tunnel is a construct that contains a constrained set of paths representing an optimized DAG from one or more ingresses to one or more egresses. In this example, R1 is the ingress, R12 and R15 are the egresses. The paths that make up this DAG, the tunnel, traverse a set of junction nodes. So the rest of the nodes in this picture, they happen to be all in that DAG here. And you can use MPLS or IP data plane, even though we are starting with MPLS, but it can be IP data plane. MPTD junction. A junction is a TE construct associated with the MPTD tunnel at each node. For example, R1, R2, R3, all those are the junction nodes here. The junction state will consists of incoming bandwidth, a set of previous hops, and a set of next hops with weighted load balancing. For example, R2 has one previous hop, 3 next hop, and if you look at R12, it has 4 previous hops as an egress junction. And each next hop is associated with a relative load share. R2 has 50% load share to R3, and 55% load share to R7, R9, and respectively. Now, provisioning this MPTE tunnel involves signaling the state associated with each junction. So this is the theory of operation. We have a tunnel originator, TO. It's basically a user, human user, or an application that specifies the intent. It provides the ingresses, egresses, incoming bandwidth at each ingress, the constraints, and optimization objectives for this DAG. And then we have a computer, or MC, that calculates the DAG, taking the specified constraints and optimization objective into account. The result is a set of junctions. And then the signaling source provisions the MPTE junction states by sending messages directly to the junction nodes. Traditionally, when you set up the RSVP tunnels, the ingress send the path message along the path, and then you get reserved messages back. With MPTE, the messages are sent by the signaling source to the junction nodes directly. And the signaling source does not have to be the ingress. It can be a controller, it could be a third party or whatever. So when all the junctions are provisioned, then the ingresses can start sending traffic into this tunnel. So signaling options, RSVP-TE signaling with enhancements is one choice. BGP signaling, which makes more sense in the data centers, is another option. You can also use PCEP. You can use programmable APIs backed by a young data model. Our initial prototype uses RSVP-TE extensions for good reasons. And we also are working on the BGP signaling as well. So now, RSVP signaling for the MPTE DAG. Why RSVP? It's a natural choice coming from the WAN background, where if you already deploy RSVP traffic engineering, extend it to multipathing, it's just a natural choice. And also notice that a bandwidth engineered construct requires reservation of resources. And the RSVP provides that. It enables distributed provisioning of MPTED tunnels. You can do it from any ingress. And the computer can be those ingresses individually as well. It enables seamless use of signals MPLS label switching that have been doing in the WAN. Enables ordered admission control and priority-based preemption, again, associated with existing RSVP signaling. Enables automatic update of link state, resource reservations. Whenever you make a reservation, the existing infrastructure will trigger corresponding updates in the available remaining resources. Also enable ordered programming of labeled routes, just like in the single path traffic engineering case. You send reserve state to your upstream and reserve message to your upstream carrying a label, and so that your upstream can reserve the resource and program forwarding state. That does not change with the MPTE. The main change is that now instead of signaling individual LSPs all the way from head, hop by hop, you signal the junction state directly to junction nodes. And obviously, if you already deployed RSVP in single path traffic engineering, it's incremental deployment interoperates with the traditional RSVP signaling procedures. So at a very high level, these are the messages involved in the junction management. The first one is a signal to junction, signaling source to the junctions. As I mentioned earlier, the messages are sent from the signaling source to each junction directly. Junction create, junction update, and junction delete. In the RSVP case, we have corresponding the RSVP, MPTE pass messages, and MPTE pass tail messages. Then we have the junction to source messages. It's really for the notify purposes. If there is something going on in a particular junction nodes, we can send some notifications to the source. And then junction to junction messages. Upstream junction to junction messages, similar to the RSVP reserve messages. And then the junction to junction downstream messages. There are situations where an upstream junction node may want to tell a downstream node that, hey, you can tear it down, you can delete your state. So in this picture, where you see the word RSVP, that's basically our RSVP specific messages, and the rest are the generic messages for the junction management. It could be signaled by other means. Going back to this earlier picture, we talked about that if you use container LSPs to make use of all the available paths, you would need 30-member LSPs. That many messages and states on the routers. But if you use MPTE tunnel, then you only need one tunnel, MPTE tunnel, to cover all those paths. It involves 46 messages, RSVP messages on the wire, but only one junction state block on each router. If you look at router 4 there, it has one junction state block with 2 P hops, 2 and 3, and 3 next hops, 5, 6, 7. And on R8, you have one junction state block with 3 P hops, 5, 6, 7, and 5 next hops, 9 through 13. Now, BGP signaling. I understand that using RSVP may be a concern for certain operators, especially in the data centers. It's probably a no-no. And data centers has traditionally used BGP signaling. We can use the BGP signaling for the MPTE junction signaling as well. In this picture, I have ingress switch L1 at the top, egress switch L4 at the bottom. This DAC involves the ingress, egress, and 3 spine switches, and 1 super spine switch, SS2. Just for illustration purposes, the spine switch S2 can split the incoming traffic into 2 ways. One going to L4 directly, the other one going through SS2, coming down to S3, and then eventually could go down to L4. Now, here, the signaling source, which could be the ingress switch L1 or a controller, will originate one BGP route for each junction. And each route is targeted at the node, the junction node, encodes the identifier of the DAC at the junction, and includes P-hop information, next hop information, and bandwidth information. And if you're using MPLS data plane, then you could use static or upstream assign label in that route, so that when you get that route, you can program all the states right there, and then you're ready to go. That's when you do not care about ordered control. But if you care about ordered control, meaning you do not set up your forwarding state or start getting traffic into that, you're sending traffic to your downstream until you have heard from your downstream. So that's order control. If you want to do that, then each junction node will originate a BGP route targeted at each of its P-hop. That's like a junction-to-junction upstream message. It carries a downstream assign label in the MPLS case. Then your upstream can set up its forwarding state. just like in the single pass case. Those routes are propagated to and then stops at the targeted node. Following the eBGP sessions, in this case, L1 sends one route to S2, or S1, one route to S2, and one route to S3, and another route to SS2, just following those eBGP session. Or you could introduce an optional route reflector so that those BGP routes are only kept under a route reflector and on the targeted route, the routers. It does not need to involve other routers in the path of the route propagation. So, come to our takeaway sections. We have seen the two domains, each with its own gap. In the data center case, we have multipath, but no traffic engineering. And in the WAN, we had traffic engineering, but we didn't have multipath. Now, with multipath traffic engineering, we have one solution for WAN and AIDC that achieves high utilization, high resiliency, provides, I would say, linear congestion-free and low latency and low loss traffic delivery. Current status, we are working on the prototype. We are talking to operators. We have got quite a few operators interested in this. So a prototype to show how it works and to show that it really works is important. So for this prototype, we have the CLI that's where you can specify the intent, ingresses, egresses, compute constraints, objectives, and then we have the constraint SPF DAG calculation written in Rust language. And we make use of the traffic engineering database, the existing one, and collected by IGP or by BGPLS. And then we're enhancing the RSVP signaling and the BGP signaling to set up the junction state. By the way, I am actually working on the BGP signaling myself as part of this project. And then we use the CLI to show the results. So you can see that those the blue colors are existing codes. We are writing the new code in the orange colors, and specifically for the DAG calculation part, we're using the Rust for that. So there are continuous investments in the traffic engineering toolkit. We still have a lot of customers still use traffic engineering, use bandwidth reservation. We are adding multipath to traffic engineering, getting the best of both worlds. We can also meaningfully add traffic engineering to network engineered for ECMP and get new value. So both paths lead to multipath traffic engineering. With the lessons we have learned from hard-earned experiences, and build a much more robust and scalable protocol for MPTE. So the goal of this presentation is to share with you this MPTE solution, the ideas, the concepts. Hopefully, we can make you consider or reconsider traffic engineering, and hopefully I have accomplished that in this presentation. So thank you. If you download the slides, there are some additional supplemental slides there following this slide. The references, yeah, the IETF draft, some presentations, and also some more details for some scenarios. Thanks.
Thank you, Jeffrey. Do we have any questions in the room?
Hi. Tom Kostrinsky, Akamai. Two questions. First one, does this eliminate the need for backup paths? And then the second question is, how do you define the junction points on the RSVP path? You mentioned on the BGP signal, you are advertising specific routes, but within the RSVP signal path, how does it know about what junction point it is and how to allocate 50 or 40% on this path and the other path?
Whether it's BGP or RSVP, it's similar mechanism. When you calculate the DAC, you already know that at each junction, how much traffic do you want to split which way. That's part of the DAC calculation.
So do you define that? Like, let's say you want this to be 50-50 versus 40-60 on each junction point?
That's probably depending on the constraints. For example, if you know that you can go through 2 paths to the destination, to the egress, but you know that on one path you only have this much bandwidth available. On another path you have more bandwidth available. So that's one input on how you can determine the split.
Okay. And then in the backup paths, do we still need those as part of this, or do you eliminate that?
Backup paths, I guess you can. It's basic. You don't really need the backups anymore, because when you have the multipath, if one path goes down, you can just go to the other one, and that's when you have when you can split the traffic. But there are scenarios where you go between two junction nodes, there is only a single path, even though the previous junction can split the traffic 2 ways. But on each way, it could be that you only have one path. There, you may need some backup paths. But I have to admit that that's part. It's not very clear to me. I am not working on the DAC calculation. So in theory, you could calculate the backup paths wherever you desire. But,
Thank you.
Thanks.
Steve?
Steve Ulrich with Nextop AI. I'm kind of curious about how you handle the MP TED in conjunction with the kind of standard point-to-point TED. So if you have nodes in the mix which are not necessarily MP TED aware or capable of announcing like junction node capabilities, do you like unify the reservation for an existing point-to-point LSP into the bandwidth reservation that you're doing in the MP TED?
I'm not sure if I've heard your question clearly or not. But if are you asking that if the bandwidth reservation used for the MPTE and regular do they interfere with each other, or
Are they unified, or in the event that I have existing point-to-point TE LSPs and I have a junction node, right? If on say an egress interface I have a reservation, and I'm advertising a reservable available reserve bandwidth, right?
Right.
Do you keep those as 2 separate entries in the TED, or do you collapse the point-to-point entry under the MP TED and forward using whatever that FEC is?
I don't have an authoritative answer for that, but my assumption is that you only need to know your remaining bandwidth that can be used for either.
Okay,
It's,
thanks.
you just
So you reuse the existing unicast, the existing point-to-point
right.
TLVs for that. Okay, thanks.
Yeah.
And we have one question from online.
From online, Matt Pitak, unaffiliated, says, good talk, thank you. Can you confirm that in the BGP signaling methodology, you're advocating doing eBGP multi-hop sessions from the ingress node to each junction node? It wasn't entirely clear from your slide. Thank you.
So if you only just use eBGP session, you do not need to set up multi-hop sessions from ingress to egress or to the junction nodes. You already have a BGP infrastructure there. Once you originate the route that is targeted at each node, then the BGP infrastructure will get the route to the targeted junction nodes, just following the existing hop-by-hop eBGP sessions. It is optional to set up a route reflector so that all the junction nodes just peer with route reflector for this BGP signaling purposes, and then they all talk to each other through that route reflector. Obviously, when you do not use the route reflector, the hop-by-hop propagation following those eBGP sessions means that the nodes that are in the propagation path will have to keep the junction routes that are not targeted for itself. So that's a trade-off there.
All right, I think we're done. Thank you, Jeffrey.
Thank you.
It's a great talk.
Thanks.